Good morning, everybody, and welcome. My name is Cara. I'm with the Bioenergy Australia team. You've probably heard a lot from us over the last few months as we've intensified our online activities in support of the industry, even during these difficult times. Bioenergy Australia is the non-profit membership association for Australia's future bioeconomy. Our member ranges from airlines to state government departments, project developers, technology providers and investors, as well as owners of infrastructure assets, just to name a few. We run a number of alliances, including the Renewable Gas Alliance, the Sustainable Aviation Fuels Alliance of Australia and New Zealand, and the Circular Economy Network. Our mission is to drive the development of the sector and to ensure that bioindustries play a key role in Australia's future. We look forward to the release of the Commonwealth Bioenergy Roadmap in the coming months and welcome any of you who are interested in finding out more about Bioenergy Australia and our membership options to contact me after the event today. Today's webinar is To Infinity and Beyond, the opportunities and possibilities for biohydrogen, and we'll focus on the key role that biohydrogen could play in Australia's energy and industry mix into the future. The webinar is offered today in partnership with the Australian Hydrogen Council and Future Fuels CRC. The webinar will be moderated by Amy Philbrook from ARENA, who is also the Australian representative on the IEA Bioenergy Task 44 and a board director of Bioenergy Australia. And we'll hear from Daniel Roberts, leader of CSIRO's Hydrogen Energy Systems Future Science Platform, Mark Jonker, founding director of Helmont Energy, and Jeff Ward, CEO and managing director of Hazer Group. Before we begin, I do want to make you aware that this presentation is being recorded. We ask that you turn off your camera to reduce distractions, and please make sure that you're on mute during the presentations to avoid any background noise. Questions will be answered at the end of the webinar. To ask questions, please type it into the chat window, which you'll find on the right side of the control panel. And with that, Amy, the floor is yours.
Thanks, Cara. And can you hear me okay, Cara?
Sounding good.
Okay. As Cara said, I work for ARENA, and I'm also a board member of Bioenergy Australia. The webinar actually reached capacity last week, which is it's just great news, and it's great to see this level of interest in biohydrogen. I wanted to start the webinar by introducing the advantages of hydrogen produced through bioenergy. This slide shows the simplified hydrogen supply chain from production through carrier to end use. The green sections illustrate how bioenergy contributes to the hydrogen supply chain. For hydrogen from electrolysis to be renewable, the electricity supply needs to be renewable. Solar and wind can provide electricity. However, bioenergy has the added benefit of providing baseload generation. The constant supply of electricity is important to the operating capacity of the electrolyzer, and unlike bioenergy, wind and solar are intermittent sources of electricity. Biomass can be converted to hydrogen through a number of pathways. There are two shown on this slide. One is thermochemical conversion or gasification, and the other is using microorganisms or enzymes. Another pathway which is technically ready to be deployed today is the production of hydrogen through steam methane reforming. But instead of using natural gas, biomethane can be used to provide a carbon negative solution. And Mark will be discussing this pathway in detail today. The pathways I have shown in this slide are the well-developed pathways. In addition to the ones shown, there are numerous ways that bioenergy can be incorporated into the hydrogen supply chain. Jeff and Daniel will be presenting innovative and potentially groundbreaking processes for the production of renewable hydrogen. With that, I would like to invite Daniel to give his presentation.
Great, thanks Amy for that intro. Now let me execute this screen sharing move, which we've practiced 3 times, and it's worked every time. How are we going, Amy? That look all right?
Yeah, that looks great, Daniel.
Okay, good. So look, thanks again. So yeah, I'm the director of the Hydrogen Energy Systems Future Science platform here at CSIRO, which is an initiative really aimed at ensuring that this emerging hydrogen industry has the breadth of technologies available and the scientific capabilities available, really to ensure its success. And we've been working now for about 3 years, and it's really interesting outcomes from some of that work in terms of potential step change technologies, which I'll talk a little bit about. As well as the leader of the FSP, pardon me, I'm also a researcher and a scientist with a lot of experience in gasification and combustion of things. And in that capacity, conversion of waste and biomass via gasification is of interest. And that, of course, offers another pathway for biomass to contribute to this hydrogen story, which is another aspect of what I'm going to be talking about today. In that capacity, I sit on, well, I'm the Australian lead on one of the tasks, Task 36, for the IEA Bioenergy, a bit like what Amy does with her task. That's a really important process for us, linking into some of the global best practice in this space. This is my version of Amy's hydrogen pathways slide, and anyone that's seen me speak about hydrogen will have seen me put this up. I'm not going to go through it in a lot of detail. I think the point is there are lots of ways of making hydrogen. There are lots of ways of making renewable hydrogen. And once we've made that hydrogen, there are many, many things that we can be doing with it, both domestically in terms of decarbonisation of a whole range of different sectors. This isn't just about transport or electricity. This is much broader than that. But there's also the renewable energy export industry vision. And I think, the point of this slide, the take-home message for me is that once we can make this hydrogen, it doesn't care where it's come from, we can use it for lots and lots of things. And, a week doesn't go by now where we don't see new examples of projects being either planned or delivered, which are all around making low emissions hydrogen at scale. And the team at ARENA has really played a significant role in advancing a lot of those projects. So kudos to them. Scale, though, is key. This is one projection of just how much hydrogen we can expect to participate in the global hydrogen industry in the next 30 years or so. This is one projection. It's a big projection, but nonetheless, it shows that a lot of hydrogen is going to be used and transported around the world for a lot of new applications. And most people, when they consider the scale here, appreciate that we're going to need a lot more than renewable electricity and electrolysis, and we're going to, both for making the volumes of hydrogen that we need, but also for getting the benefits that we hope to achieve by linking hydrogen production and use across sectors. And I think that's really a role that biomass and bioenergy can play in supporting this emerging hydrogen industry. Now, I've only got 10 minutes or so, so I don't want to dwell too long on the background. There's two parts to what I want to talk about today. I'm here to talk about what we're doing at CSIRO in this space, and there's two angles there. One is the thermochemical work, the gasification-based work that Amy referred to, and that's something that we've been doing for a long time and have a considerable amount of experience in with a whole range of different feedstocks, frankly. The other angle is some of the more emerging, interesting projects that are coming out of the Future Science platform that I run. And that's some of the biological and enzymatic pathways, which I know a lot less about, but I'm really quite excited by the prospects of. So when we talk about thermochemical pathways in a broader bioenergy context, we usually talk about combustion, gasification, pyrolysis, really in the notion of, well, for our work in biomass and waste to hydrogen is really focused on the gasification pathway. That's largely because of our experience in the gasification process, our capabilities in syngas processing and utilization, but also because of the flexibility of syngas. I mean, almost all of the hydrogen used industrially at the moment comes from a syngas, which is made from either coal or natural gas. And so using biomass and waste feedstocks to produce a syngas offers a really good pathway for biomass to participate, with the challenge being around gasifying the biomass and waste effectively at scale and producing a syngas that can then be used. We've been doing, the world has been gasifying things for a long time. Large-scale coal to chemicals, fertilizers, power, gas, hydrogen has been going on for hundreds of years. The fertilizers and the chemicals that are made from hydrogen nowadays come from coal gasification or perhaps natural gas reforming. And we have a lot of experience as well with biomass gasification, mainly at small scale for power generation. But as the world is becoming more interested in other products, there's a lot more interest in these gasification pathways due to their flexibility. When we start to consider waste, this process is much less experience, I guess, with waste gasification for syngas and other products. There are lots of concepts out there, lots of demonstrations. Some good technical success, I think, is probably where I would put this. Some challenges with project economics have been well documented, in particular for the example that I've put here. But really, that's not surprising for early stage, first generation approaches here. And I think when we get better at scaling up some of these technologies and we do a bit more work, motivated by the need for circular economy principles and other drivers, these technical demonstrations will be a lot more successful. And we talk about gasification. This is, for those that have listened to me talk about gasification, I've been using this slide for almost 20 years. And back in the day, our focus was on coal to power, with, to try and get this high efficiency, low emissions electricity generation at scale. We've moved on from that for lots of reasons, but the slide is still relevant. And if we take this waste and biomass as a feedstock here, we can see that the syngas is really at the heart of producing a whole range of different products. Hydrogen is listed here explicitly, of course. Chemicals, methanol, ammonia become really interesting here because ammonia is seen by many as a really prospective carrier of hydrogen as we start to consider exporting it around the world. And so it's this flexibility both of feedstock and of product that really does mean that gasification pathways in the context of biomass for hydrogen become really quite interesting. And the sort of work that we do here at CSIRO is focused around our research scale biomass gasifier. Around about 50 kilos an hour of dense biomass is what it's nominally designed for, but being a research facility and being researchers, we do tend to push that a little bit to try and see what we can come up with. It is it's a fixed bed style gasifier, so it's really well suited to dense materials, and we partner up with research institutes from around the world if we need to diversify our technology. Supporting this gasifier, of course, is a whole range of laboratory equipment and facilities which really do give us detailed insights into what goes on inside the gasifier, detailed characterizations of the syngas and the tar that comes out of it, which is critical to support the syngas to hydrogen pathways that we're starting now to seek to demonstrate. I'm rushing through this, I know. I'm trying to keep within the time. I'm more than happy to talk about any of these aspects either at the end or even afterwards if you want to get in touch. These biological pathways are really becoming quite interesting, and there's a whole range of different ones here, and there's no chance that I can cover off on all of them. Oh, time is one, but my knowledge of them is another reason. But really what's interesting for this discussion is that we can have these fermentative or bioelectrochemical or even enzymatic pathways that take waste streams or biomass materials and can use them to produce hydrogen under conditions that are far less intense than some of these thermochemical processes. And that's really quite attractive, I think, as we start to look for a whole range of different applications of these types of technologies. My next two slides are two examples of some projects that we're working on in my FSP. This one's interesting. This brings together two areas of expertise in CSIRO around our fermentation experience and our solar thermal experience to really come up with this concept that can take, I guess, some fairly established pathways, but tweak them so that they are well suited for taking biomass, biosolids, and waste streams, and using this fermentative process, this dark fermentation process, to produce a high yield of hydrogen, amongst other things. This has got a whole range of applications. We're talking to people now about using this in the wastewater management space. And I think getting this diversity of feedstocks working in this process via the use of some thermal pretreatment is a big what part of making this work. So that's quite interesting. Now, this is one of my favourite projects at the moment, and it's because it wouldn't have happened, I don't think, without this notion of a future science platform. It's not specifically around converting biomass into hydrogen, but it's good enough to put on here anyway. It's around taking biologically inspired materials, so these nitrogenase enzymes, which plants use to fix nitrogen, and make those industry-proof, if you like. And what that will lead to is this process for solar power conversion of nitrogen in air to ammonia and hydrogen under ambient conditions. Now, that really is a game changer, and the work that we're doing is showing that it's possible. It will work at small scale, and we can now begin to think about how we might make this happen at a larger scale. So that's my 10 and a bit minutes. Really quick overview there of CSIRO's work in thermochemical and biological pathways for hydrogen production from biomass and waste. My contact details are there if you'd like to follow up with anything. But for now, Amy, I'll send it back to you.
Great. Thanks for that, Daniel. And so I think, Jeff, you're the next speaker. If you wouldn't mind sharing your slides and introducing your company.
Amy, I think we actually had Daniel up next.
We just had Dan. I'm happy to go, Amy. I thought Mark was next. But
Sorry.
Sorry. Mark, are you ready to go there?
I am ready to go.
Okay, great. If you can just introduce yourself, that would be great. Sorry, Jeff.
Okay, Cara, can you see my screen? Or Amy?
Yes, it's showing nicely.
Excellent, very good. Well, thank you everyone for the opportunity to talk this morning, and thanks to Bioenergy Australia for providing Commonwealth Energy the chance to talk about biomethane. It's great to hear Daniel talk about the different technologies that are emerging to create hydrogen, and today what I'd like to do is focus on one of those technologies, which is biomethane. And the reason we're looking at biomethane is that we think it's got huge potential in this market to make a material difference to our carbon abatement story going forward. So the title of my presentation is Commoditising Biomethane, and you may ask why that's important to the green gas and emerging hydrogen industry. Well, the answer's simple. It's because, you know, if we can create a biomethane commodity, we can give producers and consumers a liquid market to buy and sell their product. We can open up the market and increase the participation rate by giving all gas users the option to purchase green gas. And we can give confidence to investors in the downstream clean energy technologies such as biohydrogen, the confidence that they need to invest in those technologies. So, having worked in the energy industry for over 20 years here in Australia and abroad, I know the challenges that we face to decarbonise our energy supply chain. Our reliance on cheap coal makes it particularly challenging in Australia to decarbonise our economy. But notwithstanding this, we're starting to see the tide turn, and carbon emissions in our electricity sector are now starting to decrease. This has largely been achieved by introducing gas and renewables into our supply chain, which in no small part has been helped along by our friends at ARENA, the Emissions Reduction Fund, and the now oversupplied renewable energy target, not to mention the state-based schemes that have been in operation for a few years. But our current reality is that material reductions in our emissions will only be achieved once baseload coal is retired or emissions are sequestered, and that new technology and policy frameworks are needed if we're to decarbonise other sectors of our energy supply chain, and those sectors include transport and stationary energy. We'd like to see Helmont Energy adopted here in Australia as a clean fuel energy technology. As you can see from this infographic here on slide 2, the production and use of biomethane can provide multiple benefits to many industries across the ag sector, across the waste sector, and our energy supply chain. And we're certainly looking forward to seeing biomethane selected as a priority future technology as part of Angus Taylor's technology investment roadmap. Biomethane is produced from a variety of feedstocks and can be converted into a variety of energy products to meet our energy needs. As an example, biomethane can be stored in the natural gas grid, and it can be used within peaking power stations to firm up our intermittent renewables. It can also be converted into vehicle fuel and used to decarbonise the transport sector. And I've got some slides in this pack that show just what's happening in our markets. And of course, it can be delivered to any gas consumer connected to the gas grid and used to decarbonise the energy supply. And because biomethane is interchangeable with natural gas, it means we don't need to upgrade our gas grid or our gas appliances to use this zero emissions gas. This gives biomethane the ability to do the heavy lifting that is required now by our next wave of clean energy technologies. In Australia, we've got a large supply of organic waste resources that could be converted into a biomethane resource. Most of you may have seen the Deloitte Access Economics study that was completed in 2018, which identified that there was 371 petajoules per annum of recurring biogas resources. Now, to put that in perspective, that's enough gas to meet 80% of the domestic East Coast gas demand. The waste is largely derived from our agricultural areas and our cities, which produce municipal solid waste. Currently, this waste goes to landfill, is stored in large lagoons, in some cases incinerated, and it's also returned to cropping lands as organic material. So this is my attempt at coming up with the various processes of producing hydrogen. I managed to find a really good source from a report that was completed by Shell in 2017. And I like this process chart because it just showed the various different technologies that are out there to produce hydrogen. And as you can see, where I've circled with the red circles, I'm trying to show the pathway that a biomethane to biohydrogen process would provide. One of the benefits of biomethane is that it can also be used to produce CNG, LNG, biodiesel, and biomethanol, which are all products that can be used in the transportation sector. And those products can be manufactured using secondary processing technologies. What I find particularly interesting is that hydrogen has been produced using natural gas in a process called steam methane reforming for the last 70 years. And to my knowledge, that particular process currently supplies 95% of the hydrogen currently produced in the market. And with a simple change to the supply chain, we can completely decarbonise the creation of hydrogen by using existing steam methane reforming plants. But instead of using natural gas, we could use biomethane as a feedstock. But if we're going to do that, we're going to need to create a biomethane supply chain. The good news is that our international trading partners across North America, Europe, and the UK are already doing this. They are developing biomethane projects that decarbonise the gas grid. And those projects supply green gas to secondary processes such as CNG, LNG. There are a small number of biohydrogen processes, and those secondary processes provide fuel to the transport industry. In the US, as an example, they're operating 129 plants and supplying 57 TJs into the natural gas grid. To put that in perspective, that's around about 12 to 15% of our East Coast gas demand. The green gas is largely serving the transportation industry and being used in heavy vehicles across the US and Canada. So if you've been to the US, you might have noticed that the back of the semi-trailers and the prime movies, they have CNG tanks which are used to fuel those trucks. Those CNG tanks contain renewable natural gas. The situation in Europe and the UK is similar. There are over 500 plants supplying biomethane. In Australia, but we can change that. We can change that by creating a biomethane commodity like they have in international markets, and we think that'll open up a new clean gas and fuels market here in Australia. To do that, we need to make 3 changes to policy. Firstly, we need a policy instrument that will encourage the uptake of biomethane in either the gas grid or the clean fuels market. We're pretty lucky. We already have an emissions reduction fund, and that fund could support biomethane or biohydrogen by the creation of carbon credits. And those carbon credits, or ACCUs, can be valued by investors, helping underpin capital required for new biomethane and biohydrogen projects. Equally, we could introduce a green gas target, which would set volume targets on green gas production. This would be similar to the RET, or the renewable energy target, which has successfully delivered material amounts of utility scale renewable electricity into the market. Secondly, we need to give the market the confidence that when they are buying the product, that it creates credible, internationally recognisable emissions abatement. To do this, we need to make some minor tweaks to our existing emissions reporting standard, which is called the NGRED measurement determination, which unfortunately doesn't recognise green hydrogen or biomethane as a zero emissions fuel when delivered through a multi-user gas network. Thirdly, our natural gas grids have a really important role to play. Like the national electricity market, their role is to connect renewable producers to consumers of renewable energy. Fortunately, there are proven models on how to do this in overseas markets. However, in Australia, currently when a biomethane producer injects green gas into the gas grid, it loses its environmental properties and cannot be recognised as a green gas by the consumer purchasing that gas. That means that a consumer does not get the ability to reduce their reportable emissions under our national emissions accounting methods, which is called the NGREDs. The key is to be able to inject biomethane into the gas grid, consolidate the supply of biomethane plants, and then withdraw biomethane at dedicated green gas consumers or secondary clean fuel processes such as biohydrogen. On this slide here, I've tried to capture the changes that we would need. I'm trying to show that the gas grid represents a pool similar to the NEM, and one biomethane molecule injected can be withdrawn anywhere within that pool. And in this case, the pool is the pipeline. If we can deliver on these policy changes, we'll unlock the 371 PJs of biomethane potential. We'll start to decarbonise our natural gas grids, and we'll spur on new investment in clean fuel technologies such as biohydrogen, which can be delivered using proven large-scale production technology, such as steam methane reforming, or even the Hazer process, which I'm looking forward to hearing more about in this webinar. Importantly, we give our regions jobs, and this is really important for our economy as we look to recover from COVID-19. And we reduce waste by creating a circular economy where waste is converted into electricity. But of course, the key to all of this is attracting investment, and we'll only achieve that if we value the carbon abatement or green attributes of biomethane and biohydrogen. Now, I've had a go at working out the full carbon value of biohydrogen, and I caution you that this is hot off the press, and so no doubt there'll be some tweaks to these calculations as this evolves. My infographic on slide 11 attempts to simplify all the various components of the biohydrogen equation. And in this example, I'm assuming organic waste is used to produce biomethane. The digestate, which is a byproduct of the process, is returned as a carbon soil improver, which offsets synthetic fossil fuel derived fertiliser, and the biomethane is used to produce hydrogen, which is then used as a vehicle application or exported overseas. What my calculations show is that biohydrogen has the potential to create or abate 0.124 tonnes of CO2 per kilogram of hydrogen. What that means that for every kilogram of hydrogen used, 124 kilograms of CO2 can be abated from the atmosphere. Now, I agree that seems like a really large number, but that's the thing with biomethane. It has some unique benefits which other technologies cannot bring to the hydrogen sector. It creates substantial carbon abatement because it not only eliminates tailpipe emissions, it also avoids fugitive emissions by utilising waste. These environmentally damaging waste emissions have a global warming impact of 28 times that of CO2. And obviously it has the potential to sequester carbon back into the soil and offset fossil fuel derived fertiliser. From a financial perspective, this level of carbon abatement could create around $2.50 per kilogram of hydrogen of incremental value. Now that assumes you can realise a $20 price for the carbon abatement. Now that's not a bad kicker if you're targeting a $2 per kilogram hydrogen price from domestic and international buyers. So to summarise, we can produce hydrogen from biomethane. We can do it using technologies, and we can do it at a large scale. Our gas grids have a really important role to play in delivering our biomethane to our centralised clean fuel technologies. Hydrogen produced using electrolyzers also has an important role to play for our future export industries. We have an abundance of sunshine, which gives us a competitive advantage to other countries. However, electrolyzers are currently expensive, and at a large scale, we need to redirect scarce water resources to produce hydrogen. There is no doubt that we'll solve those problems and lead the world in years to come. But perhaps in the meantime, we should make use of the bioenergy resource at our fingertips. We can create it in our regional areas and deliver it centrally to large-scale hydrogen facilities connected to our gas grids. We can use our existing infrastructure and participate on a global stage using biomethane that delivers material carbon abatement to our domestic economy. But to get things moving, we need to make some simple changes. We need to recognise biomethane and hydrogen as a zero emissions fuel when delivered in a multi-user that's network. We need to value the green and carbon attributes of the product, We need to enable our gas grids to deliver and receive the product across the gas network. And finally, we need to work with our existing grants programs to kick-start the industry, which will attract investors and expertise into our domestic market. Thank you for your time this morning. Sorry I don't have my contact details up here, but I'm sure Amy or Cara would be happy to pass on my email or my phone number so you can contact me with any questions or queries.
Yeah, I mean, thanks, Mark, and it's a great slide for that, and I think that, Cara, if it works for you, it'd be great if those slides could be sent around the webinar today. So our last speaker is Jeff, and Jeff is the CEO of the Hazer Group. Arena has co-funded a project with the Hazer Group, and so I would just invite Jeff to introduce his company and his project today.
All right, thanks, Amy. Also, thank you, Dan and Mark. Good to see both of you again, if not in person. I'll today give a brief overview of Hazer, but also mostly outline our commercial demonstration project that we're building at Woodman Point, a wastewater treatment plant.
I'm sorry to interrupt you. We're having some issues seeing the presentation. Do you mind cancelling and restarting the presentation?
Sure, let me try that again. How's that this time?
Looking good. Thank you very much.
No worries. If that's the biggest glitch we have, then we've done well. I'll like to sort of, as we go through this, think that this is sort of an example of many of the things that Mark is talking about. I'd actually endorse nearly all of Mark's comments. And there's a couple in there where I'll show some very similar figures that we've looked at in some details on the carbon abatement potential of the Hazer process. It's been an issue that we've been quietly working on. And I guess I'm a little bit torn between pleased to see that other people are twigging to its value and disappointed that it will probably bring a number of competitors into what we think is a really unique market niche. Let me just see how this works. All right, great. So what is the Hazer process? So Hazer is a listed company. Our ASX ticker is HZR, easy to remember for Hazer. And so it's fairly easy for any of you who do have any follow-up questions or want more information to go looking through our quarterly reports, through our investor presentations, and we also have a number of videos that animate our technology. We are one of the thermochemical technologies that Dan mentioned. We're not a gasification technology. We would be classified in that third tranche that he described there as pyrolysis. And in our process, we take a methane feedstock. We'll also work on a mixture of methane and ethane similar to an LNG or natural gas. But ideally, the process was initially designed around methane. And then we react that methane in a fluidized bed or a paddle tube reactor, two fairly standard, well-tried conventional designs for chemical reactors, in the presence of an iron ore process catalyst, which is a sacrificial once-through catalyst. And we break that methane, which has the chemical composition of CH4, down into two hydrogen molecules and a particle of solid graphite, which aggregates into a range of carbon shapes. The more technical word is morphologies, but aggregates into different carbon morphologies, carbon micro shells, carbon micro onions, and carbon nanotubes. So what appealed to me about this technology is that we take a single feedstock and we capture two products, both of which I would classify as 21st century products. And by that, I mean products which are likely to have large increase in market use, large increase in applications over a multi-decade range, 10, 20, 30, 40 years. And if I put that in sort of a slightly more historical context, if you could think of maybe the 19th century being the age of steam and iron, and then the 20th century we saw the uptake of aluminium, stainless steels and more exotic materials. As we progress into the 21st century, we expect renewables, hydrogen and composite materials to be more and more used as not only do we sort of decarbonise our economy through renewable energy, but we begin to decarbonise heavy transport fuels. We start to decarbonise heavy industrial sectors, but also we build more and more buildings, infrastructure, vehicles out of advanced materials, which bring with them both a lower embedded carbon footprint and lower carbon in use. So we think this is a technology which is going to have very, very strong support over an extended period of time. What we do think is attractive about it, and what has drawn us and the original researchers from the University of Western Australia down this path, is the use of a readily available and low-cost catalyst. Catalysts are commonly used in steam methane reforming, which is the traditional gas or natural gas to hydrogen pathway, but they're typically exotic catalysts, nickels, palladiums, platinums, complex alloys that have to be manufactured on a ceramic substrate. And so they're expensive and typically need to be recovered, adding more cost and complexity to the process. We think our process offers the capacity, as we develop it and as we scale it up, to become low cost because of its simple operating basis and because it uses a cheap, readily available and sacrificial catalyst. So the company and the business started off very much as a technology-driven company, but we also think you need in any emerging market innovation and how you look to enter the markets commercially, and that's led us to focus very closely on the sustainability aspects of our process, and in particular how we could not so much sort of meet the demand that people are talking about in 2030 or 2040 for sort of 500,000 tonne and 1 million tonne capacities and large import and export chains, but to really focus on what's happening in the hydrogen market now. As we transition from a very, very small niche market where hydrogen is typically used in sort of universities, hospitals, specialist applications, or it's used in oil refining, petrochemical manufacture and glass manufacture. So you've got two completely different markets. And what's emerging in the middle is this large market for transport, for energy, and for decarbonisation purposes that both Dan and Mark have talked about. And so what we recognised was that as some economies who are very focused on the hydrogen transition, particularly parts of Northern Europe, Korea, Japan, California, as they're getting going, they're getting going at small scale. And so we saw a great opportunity to bring an innovative commercial model to the table where we look to use available local biogas. So biogas primarily from wastewater treatment plants or landfills in Australia, from large agricultural waste stations, maybe in the US or in Europe. By the very nature of these locations, they've tended to, over time, become aggregated. So the days of every small council having a tip are long gone. And now we have large, quite high capital intensive, quite high capability waste resource centres that are typically shared by multiple councils, under contracts with private operators. Now, not surprisingly, both landfill and wastewater treatment plants are clustered on the industrial zones at the regional fringes of cities. And those ones are those areas are the same areas that typically also hold things like bus transport depots or freight nodal hubs, or are the base for waste fleets, dairy fleets, or delivery fleets. So we saw a great example to really accelerate the uptake of hydrogen, particularly as a transport fuel, by using our technology, which had the very attractive characteristic of capturing all of the carbon associated with its methane feedstock in a saleable byproduct, locating it at small to medium scale close to customers on the urban fringes and industrial areas, and offering not only a source of low emission hydrogen to early uptake customers close to where they needed it, so it's sort of a lower delivered cost, but also offered a service and a long-term pathway for the holders of these organic wastes of how they were going to deal with the methane that they were producing. Because one of the things Mark mentioned is we do have to create methane supply chains or biomethane supply chains, but recognising also that in many jurisdictions, and I think increasingly over time when Australia catches up, historically the way we've dealt with some of these organic wastes won't be allowed to be continued. So we won't be allowed to allow them to digest in open ponds with the methane venting. That's already mostly gone. We won't be allowed to spread large amounts of digestate untreated on fields. So there's more and more the owners of those infrastructure are also looking for a waste solution. And we think the Hazer process can bring that, both a solution for upgrading the civic infrastructure, a supply of low emission hydrogen, and a stimulus for local economy, in a classic example of circular economy and sustainable thinking. So we're very proud to announce just last month, with the support of ARENA, and in fact Amy and I worked directly on this project through the due diligence and negotiation phases, that we have reached financial close and made a final investment decision. The board approved going ahead with the construction of the first large-scale, fully operational, fully integrated example of the Hazer process. We have, through the early parts of 2019, engaged with Water Corporation. They're the government-owned enterprise that operates the sewerage and water supply system in Western Australia, and they're the operator of major wastewater treatment plants to the north and south of Perth. We've entered into an arrangement with Water Corporation where we will buy biogas from their existing anaerobic digestion units. The gas is currently partly being flared, partly being used for power generation. So we will buy some of that flared gas and convert it into hydrogen and graphite through a Hazer plant, which will be built co-located with the digesters on the Water Corporation site. We want to acknowledge our gratitude and thanks to the support of Water Corporation, who've collaborated with us on this. We actually think the fact that we've been able to work so effectively and so quickly with them is a real validation of that innovative market niche that I spoke about on the last slide. Just for context, we first approached Water Corporation in February, March of 2019. We had an MOU with them by May 2019, which gave the impetus for our successful application to ARENA for grant funding. And we were able to execute binding agreements for access to their site and project collaboration arrangements and supply of biogas by January this year. We are now moving forward into the design of this project. The project will produce 100 tonnes per annum of hydrogen. To put that in context, that's enough to support around about a 10-bus fleet if we can link up with a transport customer, or around a sort of a 10 to 15 truck fleet. We are currently now in the process of completing permitting approvals and placing orders for the major equipment components of our process, hydrogen purification units, reactor vessels, gas compression skids, CO2 removal skids. And we're working with an independent engineering firm out of Perth, Hazer Group, who've been our engineering partner through the design phase since June 2019. And who we've appointed as our EPC contractor. The reactor is a pressurised fluidised bed reactor using iron ore process catalyst. And for this first project, we're using electrical heating, which has many both emissions benefits in the long term, but also is a sort of growing trend in the chemical process industries to look at high efficiency electrical heating in place of gas heating. Just do want to acknowledge the support of ARENA. The project has a budget of $17 million. We anticipate it being in operation in mid-2020. Of the $17 million budget, around about just slightly under $8 million will come through an ARENA grant in the capital phase. We'll have some further funding support through the operations phase, with the balance of funding being supplied by my shareholders. We completed a capital raising in July this year to raise in total $9.4 million. And we also have drawn down a debt facility against our future research and development tax incentive claims. So the project is fully funded, and we're now moving forward into procurement fabrication. We'll expect installation activities to begin in early 2020. Just want to touch on one other point, which maybe sort of illustrates a couple of ways in which the industry is developing. And also, I think, picks up some of the, another example of some of the points that were in both Mark and Dan's infographics, which I thought were fairly illustrative. As well as developing our commercial demonstration plant at Woodman Point, we also have just kicked off a feasibility study with the consulting group Oricon and our study partners Macquarie Group and Hyzon Motors into establishing a renewable hydrogen refuelling hub in Mandara. Mandara, for those who are not from the West, is a regional city approximately 100 kilometres south of Perth. The aim of the study is to aggregate what we see as quite strong early stage demand in that region, which could be supplied from an expanded Hazer process in the future or from renewable backed electrolysis. And this, I think, is showing that's what's starting to happen throughout the hydrogen industry in Australia, that we're seeing production projects, production demonstration projects, such as our project or the Gemina project in West Sydney, also supported by ARENA, or the AGIG projects, that's the Australian Gas Industry Group projects in Adelaide. We're now also starting to see significant interest in what I'd say is hydrogen use projects. So we have the Mandara refueling study that we're doing. There was an announcement just this month about FMG, the large mining company, moving towards hydrogen buses for their Pilbara workforce. And there's also been announcements about the establishment of a fleet of refueling, a fleet of hydrogen cars and a refueler in Western Sydney. And this is really consistent with what Professor Finkel advocated in his National Hydrogen Strategy, that we should seek to accelerate our support of development projects that would show proof of concept, proof of technology and increase awareness, and that we should try and cluster together these projects to create hubs that could then drive commercial models and scale. So appreciate that the focus today is of bioenergy, and I think that was well covered by Dan and Mark. And then coming downstream from bioenergy, we're seeing an enormous opportunity in the hydrogen space, both in the production and use of hydrogen, that's starting to be catalysed by sort of fairly consistent and sort of logical efforts of government at all levels and private industry. So I might stop there. We're delighted to showcase this as a large-scale hydrogen project, but also as a really innovative bioenergy project. And I'll hand it back to Amy.
Thanks, Jeff. Yeah, it's such a great project, and thanks for the additional context on upcoming uses of renewable hydrogen. So I just ask everyone that has questions. We have about 10 minutes for questions to put them in the chat function. And I think I'm just going to go from top to bottom. So Henty's asked, how actively is microalgae pursued in Australia as a source of biomass? So I can have a go at that one. So I guess about 10 years ago, alongside the rest of the world, Australia did pursue microalgae as a source for energy. And in general, and kind of emphasize in general, microalgae the markets have moved away from kind of this large scale energy source to more niche markets like nutraceuticals, their ability to bioremediate. So there has been, I guess, less of a focus on microalgae for bioenergy uses, but there's a definite market for other higher value products. There's a question from Greg, and I think, Mark, you might have answered this. What's the current benchmark price per kilogram of methane to make this all worthwhile? And I think he asked the question when you were speaking.
Yeah, it really depends on carbon abatement component of the process. So if you take that example which I used for the slides, if you're targeting a $2 per kilogram hydrogen price, the total cost or the total price for the biomethane to hydrogen methane reforming process would have to be around sort of $4.50 a kilogram, which is about $33, $34 a gigajoule. And from my understanding, steam methane reforming can be done at a small scale at around $25 a gigajoule, and that assumes that you're buying natural gas. So there's a little bit of a buffer there which would help recover the additional cost of collecting waste and producing biomethane. So, but Gregor, I'm happy to give you a call or later on this afternoon. I can explain it further to you.
Great, thanks. And another question from me, and maybe might suggest Jeff on this one. Are the policy regulations in place to use hydrogen as an alternative fuel in Australia? And what is the current price?
I'm sorry, Amy, that question distorted as it came through to me. Could you just please repeat it?
Sure. Are there policies, regulations in place to use hydrogen as an alternative fuel in Australia? And what is the target pump price of hydrogen?
Right. So, in short, the answer to the first probably explains why there's not a clear answer to the second. So, no, there's no real policy framework to encourage the transition away from diesel in heavy transport in Australia. In fact, that's if anything, we have a policy framework which incentivise people against it through things like diesel fuel rebates. And Australia is quite unusual in that we're the only one of the OECD countries that doesn't have some sort of vehicle emission standard. And so this is actually one area of enormous opportunity. So we can reduce the cost of our fleet by improving fuel efficiency. That's been the experience in Europe, the US, and other places. But we've resisted doing that from a policy perspective. In terms of what's the target pump price, our analysis we've seen from other people in the market indicates that while diesel is sort of sitting anywhere between sort of $1.20 to $1.50 a litre in recent times, that hydrogen is very cost competitive with that at current prices and at current technologies. The pump price break even for diesel replacement is probably somewhere in the order of $10 to $15 a kilo at the pump delivered.
Great, thanks. And there's a question from Dawn that I think that Daniel's answered, but might just ask Daniel if he had anything further to add on the use of pyrolysis versus kind of traditional gasification.
Oh, look, it's as I said in the chat. I mean, you can definitely do it. It's not impossible. Pyrolysis is a lower temperature process. The gas produced is much more diverse in what it contains. There's lots of tarry materials, larger hydrocarbons, those sorts of things. And so to make hydrogen, there's a lot more work to do to tidy up that gas and to get the hydrogen out of it. So if hydrogen is your product and there's nothing else of material interest, then gasification pathways are probably more likely to be effective. I noted in a follow-up question, the context was around a biochar facility. So they've already got this pyrolysis process making biochar, and they're seeking to get some hydrogen from the off gas of that, which of course shifts the pros and cons a little bit. But yeah, pyrolysis does need a pretty homogeneous feedstock and a good degree of gas processing.
Great, thanks. A question, I think, for Mark. Are there currently projects commercialized where biomethane is converted into hydrogen through SMR? And I think the basis of this question is, can small-scale SMR units be a solution to localize hydrogen production?
Thanks, Amy. So my understanding to that question is yes, there are small-scale SMR technologies available. Those technologies are largely run on fossil fuel-derived natural gas. And to my knowledge, there's one, perhaps two projects in California that are taking biogas sourced from landfill to produce biomethane, and then converting that biomethane to hydrogen. And instead of running heavy vehicles on that hydrogen, the hydrogen is being used to run forklifts. Now that's my only reference site. But I guess the difference in the States and European markets to what we're trying to achieve here is that those markets are producing renewable gas, and they see that renewable gas as a renewable product and a clean fuels product. So that extra step of converting it to hydrogen doesn't create any additional carbon or green value in those markets, the way those policy instruments have been established. So those markets are very much focused on biomethane, renewable natural gas, as opposed to taking that next step and converting it to hydrogen.
Thanks. There's a question. Is there an incentive for aggregated waste residues from the hinterland? And so I might just suggest that you follow up with Cara on that question directly following this webinar, and maybe provide some additional context in which suggests that Bioenergy might be able to point you in the right direction. What else do we have? There's a question. There's a suggestion about some information from some work done in Germany that's in the chat. And so would suggest that if you're able to send that work around, we can distribute that, Anthony. Henty has another question. When do you expect the Hazer technology to be ready for small-scale commercial operation in South Africa? Any plans for that market yet?
Well, I'm presuming that one's directed to me. We haven't focused on South Africa. What we see in the sort of the shorter stage is you're looking for markets that have strong carbon regulation in some of the points that Mark referred to, and you also have really well developed waste industries, because that sort of creates the existing infrastructure to provide biogas. We think we'll be ready for commercial operation from 2023, 2024, and that means not starting to look for projects then, but actually having projects into construction and looking to come onto line and on operations. We've got an MOU with Chiyoda Corporation, who would be the leading hydrogen engineering provider in Japan, to talk to local governments and prefectures about projects in a similar model to what we're doing with Water Corporation in WA. And we're sort of seeing a lot of inward interest from international markets, and we would hope and are targeting converting one or more of those opportunities into commercial scale projects in parallel with the proof of technical concept and proof of commercial concept through the Australian project.
Thanks. So just another one, Jeff, and just realizing that we've gone over time, so might just answer a couple more questions, and then Cara and I can sort through the rest of them and get responses following the webinar. For the Hazer process operation, how do you deal with the change in quality of biogas?
We pre-treat the biogas to remove the CO2, siloxanes and sulfur compounds. And that's one of the things that I guess is slightly different from sort of, the current commercial model of dealing with most biogas in Australia, which is combusting it through a converted diesel engine, through a gas engine for electricity. We see the higher value of both hydrogen and the graphite byproduct, we believe is going to be able to support the pre-treatment of the biogas, so you actually get a pure biomethane stream into your reactor.
Great. And so Peter has some, I guess, more comments around pricing of electricity and the cost of hydrogen production. And so his question actually is, localized power can be made for 6 cents a kilowatt hour, which means hydrogen would be $3.30 a kilogram. And he's just asking if those numbers are correct. I would kind of invite any of the speakers today to comment on that pricing.
Yeah, look, I might have a go at that. So, Peter, I think your conversion to hydrogen is probably correct. I haven't got my cheat sheet in front of me, but I guess the major cost of producing hydrogen is the cost of putting the capital on the ground for the electrolyser, as well as the cost of feeding it with water. So those costs are significant, and if you're using renewable electricity, which is intermittent, you're not able to utilise that equipment 100% of the time. So that's the challenge for that particular technology, is the capital cost associated with electrolyzers and the water that's needed to be converted into hydrogen.
All right, and I think I'll just end on kind of a tricky question here about, why is there interest in biohydrogen when renewable natural gas as a fuel can solve some of these issues? So we'll just invite any of the speakers to kind of comment on, why. I think the question is why go to hydrogen if you can use the methane directly?
Oh, absolutely. I mean, just because you can make hydrogen doesn't mean you must. I think this is we often sort of have these discussions in the renewables or the bio sectors, don't we? Around, it doesn't have to be our winner here. I think it's about diversifying the pathways. And so, if you want methane, then absolutely use the biogas and the renewable methane that's available. I think this methane to hydrogen option allows then for a greater market for that. So it allows a participation in a much bigger global export industry, and so it's just one more feather in the cap, bow on the quiver in the pack. Anyway, whatever metaphor you like, it's one more option. I think is how I see it.
Yeah, great. And I think that sort of answers the next question, and that's around the CSIRO's latest report on hydrogen for airports. And just the question is around investing in biofuels or biohydrogen, or do they kind of coexist? And I think it's for you, Daniel.
Yeah, I'm reading the question because it was just a little broken up when you were talking. Biohydrogen, biofuels. Oh, look, I think there's a technology, there's a TRL difference there at aviation scale. I think, but again, the aviation sector's big, and I think my previous answer around more options, more pathways, greater cross-sector engagement is relevant here as well.
Great. So on that, and given that we've gone over time, I just want to thank everyone for attending today. And I saw the slide decks before the webinar today, and it just, I just think it's such an interesting topic. Such well presentation today from Jeff, Daniel, and Mark. So thank you guys for doing that. And really, quite interesting as well. And so, as I said, Kara and I will go through the questions. If there's anything that we haven't answered or followed up on, we'll do in the upcoming days. So yeah, I'd like to thank Kara for putting together like a webinar, and it went really well and smoothly. So thanks for that, Kara. And thanks everyone for attending.
Thank you, everybody.
Thank you.